new episode of AI Chronicles, everyone. Longer days in this side of the world kind of makes me happy. No more seasonal depression for here. Well, before I start into today's conversation, I would like to share about why I decided to choose this topic and my guest. You might have read about how AI is progressing in detecting cancer cells through radiology or MRI reports. I used to really wonder how helpful is that? Or how is AI helping automate these tasks and helping cancer researchers around the world? Several other such questions. So, to answer such questions, I invited Dr. Mirabella Rusu, an assistant professor at Stanford University. Hi, Professor. So glad to have you here today. How are you doing?
Sanam, thank you so much for the invitation. I'm doing great. I'm happy to be on your podcast and hopefully be able to address some of these questions.
Absolutely. Well, without further ado, let's get started. First question, could you tell us briefly about the work you and your team in the radiology lab at Stanford do?
Yes, of course. So my team at Stanford has been focusing on developing AI approaches for improving the interpretation of radiology images. That's kind of the highlight level description, but generally what we mean by that is that we tend to develop techniques that are going to localize cancers on radiology images. We have a particular focus in that we use multimodal data. That means that we focus on getting those lesions identified on radiology images because we really believe that that's where it can affect the care of the patient
Hmm.
with a high impact. But we want to make sure that we get the best data that we can for this model. Specifically, we spend a lot of time in figuring out what's the best way to label our data and how's
Mhm.
the best way to actually extract more information from this radiology images in a context in which we have this beautiful data sets. I'll go a little bit more into the details about it. So one of our expertise has been in the integration of radiology and pathology data. So imagine that a patient has a surgery. They will
Mhm.
get a series of radiology images before the surgery. These images will indicate that there is cancer, and then there is a need for a treatment. For instance, in the case of the prostate, one of those treatments is the radical prostatectomy, a procedure that completely will remove the organ, the prostate, from the patient. Along with the organ comes the cancer, of course, which is a very effective way of treating the cancer. From our perspective, now we have this tissue that is the entire prostate that is processed in a pathology laboratory. But what it will provide to us is a nice sampling of that entire organ section very systematically. The beauty of this from an AI perspective is that this pathology image is kind of the ground truth. Of where the cancer is. This is a different modality than the radiology images. Because it's a tissue that was already removed from the patient, it can be cut and processed and fixed and all kind of these processes that will allow us to get that information about the tumor cells, and
Mhm.
then also get that information whether a certain type of tumor is aggressive or indolent, and many other things that we can extract from this pathology images. We have focused for now only on the part where we look for parts of the tumors that are aggressive, that are invading the tissue around, and some that are indolent. And these are kind of going into that idea that tumors are very heterogeneous from like kind of molecular perspective. But going back, we have this pathology images that are beautiful, high resolution.
Mhm.
And what we have done is that we register them to the radiology images acquired before the surgery. So practically what it means is that we align this beautiful image with cancer outlines onto the radiology image. So now we don't have the radiologist as an intermediate into
Mm.
how we interpret this radiology image. We have what clinically is known as being the ground truth, which is the pathology image. So when good, we have a registration between those two. We can take the labels from the pathology image onto the radiology image. We know exactly where there is cancer. Of course, we have trained some of these AI models to detect these lesions based on these labels.
Mm.
And we took that one step further and we thought about the fact that we have this beautiful data set where I know now matched regions within the pathology image, which I see a very high resolution, how the tumors look like, and I have the similar part in the radiology image. So that also meant that I don't only have the labels, but I have matched pixel, which is very unique, because now I can apply correlation approaches that will allow us to essentially extract more information from the radiology image in a fashion that has something to do with how these images appear in the pathology, or how this information appears in the pathology images. So that was one of the contributions that we have made to the space of prostate cancer, and allow us to better distinguish this cancer and localize them, and also start looking for that heterogeneity that I mentioned, where we have aggressive parts which we hope to find in a new patient, so we can actually guide the biopsy.
Mm-hmm.
So a big portion of the research that we have been doing has been focused on that. And after, since this methods have been developed a couple of years ago, we have shifted a little bit our attention towards even more clinically impactful problems that are focused on the use of ultrasound images and AI for ultrasound. Now, in the space of ultrasound, as you all know, ultrasound is very commonly used in clinical care, but those images tend to be extremely noisy. So they're hard for the human to interpret, and similarly, they're a bit hard for the AI approaches to interpret. So
Mm-hmm.
we're still kind of trying to figure it out when it comes to ultrasound, and how to best label them, and how to best take advantage of that information. But those have been some of our contributions in the space of AI for radiology images.
That's really cool and very passionate. So what are the potentials? You mentioned some challenges that you may face where it is difficult for humans to identify certain labels. So of course it is difficult for AI as well. But what are the potentials of AI do you envision helping at medical community, for example, in the cancer detection that you guys are doing?
So I think there are many opportunities here. I think AI approaches in the big scheme of things can be used as second readers, right? They can help clinicians that might have doubts about some of the things that they're seeing on the images, to get a second opinion, if you want, on some of those. It might even help them with triaging some of the cases. So those are just kind of classic examples with very low clinical impact, in the sense that they will affect the patient, but not in a fashion that disturbs what currently clinically is done for that patient, which I think is kind of important as we are developing these AI approaches. We cannot just assume that they're going to go and replace the radiologist. It's a very complicated space. There are many things that can affect how radiologists look at images, but also how AI approaches interpret these images. So I think we need to start by having them have little impact, or at least have the human as a second, as a
Mm,
person in control, before we do anything beyond that. But I think those are kind of some small low hanging fruits. Again, I am very passionate more recently about this idea of using ultrasound, and
mm.
then the fact that this modality is extremely commonly used for care for many reasons. And I believe that as AI experts, we should do everything we can to improve this modality and its interpretation.
Definitely. Yeah, I think from what I understand, what you're saying, that using AI as not giving the entire first hand to full control to AI, but just using it on side as we humans progress. That makes sense. And yeah, so moving on to a little bit what you mentioned earlier about labeling the images, the radiology
Mhm.
images or even ultrasound. So I'd love to know, like, how does this labeling really work? Is it like human labeled, or are you labeling, or you automating using AI algorithms?
Very good questions. It really depends. I think everybody that does AI for radiology images tends to have a variety of approaches, a variety of labeling strategies. We are very fortunate that in our data, we do have the radiologist outlines of cancer, because they are being used to guide the biopsy procedures. So we know exactly what the radiologist has done for that patient for clinical care, and we can use those already to start our developments. Now, of course, we also know that when it comes to prostate cancer, now a specific case, but I assume many other applications have similar problems. radiologists are picking some things that are not cancer. We call them cancer confounders. So we tend to, of course, get rid of
Mm.
them in our training. Those are not cancers. They're just things that kind of look like cancer, but after biopsy, they turn out not to
Interesting.
be cancer. And then there is the second category, the false negatives. The radiologist also miss things. And those are not very, very common. They, of course, happen, and they have certain characteristics that make them such as that they're hardly visible by the radiologist. So we deal with that, and that's the reason also why we went to the pathology data. Again, so we have these patients that have biopsy at our institution, which is great, and that we have the radiologist labels, and a subset of those are the ones that will go for treatment because the biopsy shows that there is cancer, and then we'll have these beautiful pathology images that I mentioned at the beginning. Now, because I do have the pathology images, I can compare between the two of
Right.
them and see what the radiologist has achieved compared to the pathology images, how many false positives they had, how many false negatives they have, what's the characteristic of these lesions. So that's kind of the nice thing about our cohort. Now, but of course, that also means that somebody has to label our pathology data. And pathology data is notoriously tedious to annotate. It's not necessary, particularly, I mean, you do need a pathologist to do that annotation. That's one, but it's not only about the fact that you need a human to do it. These images are huge. If a radiology image is generally about 512 pixels by 512, and you can annotate a lesion that is 1 centimeter with on one
Mm.
slice very quickly. On pathology, a pathology image of the prostate can be easily 100,000 pixels by 100,000 pixels. Well, that means a
Mm.
lot of data. And
Yeah.
then that also means that you have such a huge resolution. Beautiful. We love it. But you can see nuclei of cells, of cancer cells. Well, as you can imagine, when it comes to cancer, you have some cancer cells that are kind of everywhere. So if you really want to be very good about outlining everything that is considered to be cancer, that is a lot of pixels and regions
Mm.
that need to annotate. And that's only one image, because this is a 3D dimensional data set I mentioned. You kind of have a nice, this sequential data. So it's tedious. But of course, AI for pathology has been around forever. And
Mm-hmm.
so we have been using actually an AI for pathology to do our annotations of cancer and its grades on the pathology. We don't develop those because we do rely on people that have been doing that for decades now into detecting or essentially doing Gleason grading on the pathology images. So we relied on existing software to do the labeling on the pathology side, with understanding that even if it has some errors, it doesn't need to be perfect, but because the resolution is so different between the pathology image and the MRI image on which I'm going to project these pathology labels, those really fine details are not going to matter in the big scheme of things, the errors that we would have on the pathology side in labeling. And moreover, we have a variety of studies in that space where we show that the AI approach on pathology works comparable with the pathologists that we have on our studies. So we have no concerns to really believe that there is any that there are any concerns on the pathology labeling. So that's how we can do. We have AI labels on pathology, we have radiologists on the radiology side, and we have this variety of labels and data to test our approaches. And one of the studies that we have done, we have actually trained all these AI models that we talk about the detection of cancer
Mm-hmm.
on MRI using the different labels. Now I have a variety of labels. They have different characteristics. We have the radiologist, we have the pathologist. We also have the pathologist as well on all our data. And then we have this, we call it digital pathologists. We like to call them as a digital pathologist just to kind of simplify how we think about them and how we refer to it. But they are AI approaches on pathology. And we showed that for different tasks, we want different labels. So if we really want to just detect the lesion, we can use radiology images. Of course, the radiologists are seeing the signal in the data and they are capturing, they're very good. Even if they're not perfect, then they have false positives, they're still quite good to train AI approaches with those labels, of course. And then, but if we want to be able to characterize this heterogeneity between the within the tumor, then we absolutely need these more fine-grained labels that come from
Mm.
pathology and then from AI on
Yeah.
pathology.
Got it. So it's like a full-fledged well balanced labeling process when it comes to
Mhm.
just humans and AI doing everything. Pretty good.
Right.
I bet the training would be much easier after that.
Mhm.
So speaking of your recent the study that you mentioned about the prostate cancer detection, I came across your most recent publication about it. So I'm curious, like what AI algorithms or techniques did you use? Or and yeah, let's start with that.
Generally, when we develop AI approaches for with the labels. We start with very basic networks. We definitely started with the UNets, and then we kind of
Mm,
progressed to deriving certain networks based on the holistically nested edge detector, kind of taking advantage of their ability to extract more edges and whatnot. We have tested over the years. We have played with a variety of networks. I think the most recent developments, we are definitely working on using foundation models for some of this, extracting more information from this images and creating features,
mm,
and some of the diffusion models to kind of take advantage of knowledge that we have about how this prostate cancer are localized within the prostate and take advantage of this to train some of this more advanced diffusion models. So we really have the the really we go from the basics to the more
to
advanced,
the more
and
advanced.
taking advantage and taking advantage of all the data and the knowledge that we have about the space.
Makes sense. So from what I understand, so it's a lengthy process, or I'd say it's a I mean, it makes sense given the sensitivity of the subject matter. So, what are the biggest challenges that you may have faced, especially when it concerned to the study that we are talking about?
I think training these models is generally relatively straightforward. Getting the labels is a very tedious process. Getting
Mm,
good labels is even more tedious than just getting some labels. So I think that process is definitely always challenging. It takes a tremendous amount of effort to do all this between the different steps that we have been talking about. But I think with enough time and resources, one can and undertake that. I think we are in a kind of a good situation where we do have the radiologist labels outlines
mm,
available to us as well, right? Which would be the first line for
mm,
developing this AI approaches. So I think that's good. In a new project, in a new organ, I think that is definitely a big challenge. Is getting data is not hard. Getting data, we can request it and we can find it and whatnot. Labeling it in a fashion that actually really
mm,
captures cancer and not any other things that might be cancer confounders, I think are very different problems. So I think labels are one aspect. And for starting new projects generally, I feel like the number of patients that one can include, because we
mm,
would love to start other projects. So I do think on the prostate MRI, we've done a lot of progress. Um, and I think there that problem is from our us perspective pretty much, I would say, solved from an AI perspective. We have a variety of models that can do a variety of things, and we are in the process of actually starting to look at them from a prospective perspective, where we essentially run them on new patients and then
mm.
and see how they help the radiologist interpret their images. We're looking at that for the prostate MRI side. But on the ultrasound side, things are very different. The ultrasound
Mm.
has a lot lower signal to noise than an MRI. The detection models are not as good as on the MRI. And I think there are a variety of other challenges. So I think each project and each modality has their own challenges. And along with it, I think each data set has their own challenges. I think we always need better labels, but even when we have them with modalities like ultrasound, there is also a question: is there enough information in this ultrasound image to be able to perform this task? Which is usually not really the problem that MRI generally has, at
Hmm.
least for this task that we are generally looking at.
Nice. Okay. Yeah. Yeah. Every method has its own pros and cons, right? Uh,
Right.
that makes sense. So, speaking of these AI algorithms, what are some other examples of, for say, computer vision and even natural language processing techniques have you used and have proven useful to your work? This is just my technical curiosity now.
That's definitely a direction in which we have started to look. Um, we are not NLP kind of folks. We don't develop NLP approaches, but we did had a project recently that involved NLP where we started small. This was a little bit before ChatGPT, where we
Hmm.
started small and we're like, well, we have a small cohort, but we need to label it, and we had the reports, and of course we needed to kind of figure out where are these lesions, where are this.
Mm.
How do they look like when we look at pathology? We have very similar problems, and this is actually a project that was on breast cancer. So we were looking at breast cancer MRIs and MRI reports, and we started using some of this traditional more NLP approaches. We didn't have enough cases to train an NLP model ourselves, so we were kind of unfortunately set to just use one. We were lucky enough that ChatGPT came out around when we were trying to wrap up this
Mm.
project, and we are like kind of disappointed that it's really such a hard problem to interpret and find all this information in the radiology reports, because humans write their reports in a fashion that is not always consistent, especially for outside reports. So we came up about so then ChatGPT came around, and we had a thought about, okay, we're trying to figure out these lesions. Can we have, okay, this patient has 3 lesions mentioned in this report, and kind of spatially where they are located, so we can match them with the radiology images. So we have done that with ChatGPT. We realized that we can actually use ChatGPT for that. Essentially, give the little portion of the report that describes where the lesions could be, and say, how many lesions do you have? Where are they located? What's their characteristics? Which are something that is very basic, but not surprisingly, ChatGPT actually did very good. And we have started using it for other projects where we needed labeling from radiology reports, because ultimately there is a wealth of information that is available in these reports that need to be parsed and could be useful for radiology images. So I think that has been kind of our experience with this with the NLP approaches. Um,
Mm-hmm.
but beyond that, beyond kind of extracting, helping us do more systematic evaluation of our reports and see how we can get some of this information out of the reports, has been kind of our direction for the NLP approaches.
Nice,
We
nice.
have
I
tried
can.
we have tried a variety of the language models, the of course
Yeah.
along with
Mm-hmm.
ChatGPT, like the alpaca and all of the other ones,
Mm-hmm.
or a few of the other ones as they were coming out. Um,
Yeah, there are so many. But yeah, good to see how ChatGPT is helping in this in the radiology reports. That's a pretty cool use case, I'm sure. So, just curious, would you say, because I know you know, your lab and your entire team basically does a lot of research into
mm.
radiology pathology fusion. So, would you say that the work that you're doing is more in research phase currently, or is it being used in hospitals or other cancer institutes?
At this moment, we are in process of getting them implemented in
Mm-hmm.
our institution, so we can
Very
test them
nice.
in a prospective fashion,
Mm.
and then be able to do those studies where we do show the benefit when to radiologists when they interpret these images.
Mm-hmm.
So that's something that we definitely are looking at. Recently, in the space of prostate cancer, there's been one of these public challenges called PICI, and
Okay.
this challenges was has been very interesting, and we participated. We're the only American team that made it in the top 5. But the beauty of it is that they selected the teams, and they created this a variety of models around it. It's a beautiful study. If we are interested in prostate cancer and the radiology imaging AI, it's beautiful. But they, for the challenge specifically, they gave us about 1,500 cases to train our models, and then they essentially chose out of all the teams, they chose the top 5 teams, and then they train a model with our 5 models provided, the top
Nice.
5, with 10,000 cases 5 models, obviously different from each other because they have
Yeah.
internal data. They couldn't share all their internal data, but they could take the models and train them internally, and they did. So now they have essentially created this beautiful model trained with 10,000 cases with a lot of vendors, different types of data set. And in parallel with it, they also have a subset that is reviewed by 62 radiologists. It's a beautiful study.
Whoa. Nice.
About 400 cases, I think, were the ones that, including the radiologists. And of course, now with this, they can compare the top 5 teams with the radiologist consensus, and then essentially kind of figure out it is to a certain extent the best case scenario, right? Where you have
Mm-hmm.
a ton of, like, you have the radiologist that you can compare with, you have the best AI approaches, at least compared to this on this scale. And I think that has definitely been a very, very interesting study. So in this context, I can kind of say that our model is not really used outside our institution, but it kind of starts to grow
That's
and be part
right.
of these other models. And I do know that the organizers of the challenge, they did say, well, they cannot really release the weights of the model. They will probably make it available through a web
Mm.
interface where people can upload their MRI images or an API and then essentially run their model, kind of run that model with whatever radiology images they want.
That's good. That's good. At least it was, if it's not directly, then it's somewhere, getting
Yeah.
there in that some twisted fashion. That's really good. Yeah, this was a wonderful discussion. But before we end our discussion today, I would like to ask you one last question. So,
Mm-hmm.
what do you think is the natural step in the development of AI, especially for cancer detection?
I think cancer is a very complicated disease, and
Mm.
I think there are easy things to do, which are what a lot of the AI approaches have been focused on, which is, for instance, detection of disease. So you can help with the biopsy procedure and whatnot.
Mm-hmm.
So I think that's kind of like the lowest hanging fruit. But if you look at the clinical space for cancer, as soon as the cancer is detected, there are a ton of other things happening, right? And we
Yeah.
know there is the treatment, there is the if disease comes back, what happens. So there are really a variety of tasks that are still expected to be addressed very well. And it absolutely needs the collaboration of multiple institutions, because even if I look in our
Mm.
institution, we have a large number of patients who get a biopsy here. We have a smaller number of patients that get like the traditional treatments, but then you have even a smaller cohort that get the more newer treatments. And then from an AI perspective, of course, I don't want to do training with 100 patients. That's not sufficient. But I do believe that through the kind of combination and having multiple teams collaborate and multiple institutions essentially providing data, it can make this approaches a lot more generalizable, because we can all
Mm.
train these models in our little sandpit
Right.
and have our model that works well on our cohort, uh,
Mm-hmm.
but having them like outside is and having the data from other institutions. So I think there are many aspects that are still uh, need attention, and even the diagnosis, I think, is like there are really many. But I think the way we can um is we can go for them is making sure that the data is collected, and then the labels are somewhat systematically provided, and all of those things that will help data scientists essentially train these models, because there is a reason why there is not a whole lot of AI for ultrasound. It's just such a tedious modality in terms of how it is saved and how it is processed and how it looks like. And there's a huge variety of in like how the humans like to look at them and all of those. So
Right.
collecting good data will allow us to actually start addressing the different clinical challenges that ourselves we see as patients, and then our collaborating clinicians see as well when they are seeing their patients.
Makes sense. So I guess there still need some work. There's still need of some more work done to be
Hmm.
in the labeling side or creating that training data side in healthcare or cancer detection to be specific. Great. That's a wonderful job that you and your team are doing. I bet the research is very essential. Yeah, thanks a lot for sharing what you're doing and what you intend to do as your team. It was a lovely conversation with you, Doctor.
Thank you, Sanam, very much for the invitation. It was lovely chatting with you, and yeah, I'm happy to chat further about any of these topics. So thank
Yeah,
you again.
absolutely. Thanks.